matrix stiffness method. In the last module, I have discussed with you the matrix flexibility method and this is stiffness method. There are two concepts which differs here. If you assume a unit deflection in the structure, 1 mm deflection, if a beam is given to you, on how much load the beam is deflecting 1 mm, that is unit deflection. This is called stiffness method. And you have force method, that is matrix flexibility method, so which is discussed in last module. Okay, now let us see the basic concept. Here kinematic indeterminacy of the frames and beams are discussed here. In the last module you would have found first step as finding the redundancy of structure. So how will you find redundancy? If this is the case, you have a fixed beam here. How to find the redundancy? Number of support reaction. You have 3 number of support reaction and here you have 3 number of support reaction and you can add that. So totally you will be having 6 minus 3 will be, your answer is 3. So 6 minus 3 will be 3. So your redundancy or indeterminacy will be 3 in matrix flexibility method. This beam has a kinematic indeterminacy. What does kinematic indeterminacy is? The term kinematic indicates that movement. So in engineering mechanics you would have studied that how many possible ways for a support to move is known as kinematic indeterminacy in this chapter. And does the fixed end moves? No, the fixed end doesn't move either horizontally, vertically or even a moment can move. So there is no movement in the structure, hence you have zero kinematic indeterminacy. And for another support also you have 3 number of reaction, that is vertical, horizontal and a moment. So if you are applying any force, does the force makes the support to move? The answer is no. So your kinematic indeterminacy for the structure 1 is, for the fixed beam is 0. This is the way to find the solution. Right now I am discussing the formula, that is number of degree of freedom minus number of supports. So for a joint you will be having 3 degree of freedom and you have 3 number of support for this case and you can proceed with that. Okay, now take down the second case. You have 2 number of support. How many degrees of freedom will be there? Per support you will be having 3 number of degree of freedom. So 3 plus 3 is 6 here. And how many number of support reactions are here? This is a hinged end, you have 2 number of reaction and this is also a hinged end, 2 number of reaction, that is 2 plus 2 is 4. So 6 minus 4 will be 2 here. So your kinematic indeterminacy is 2. What does it mean? This beam is being able to displace in moment. It can rotate. So this moment can kinematically indeterminate. That is, it can rotate in clockwise or anti-clockwise at both the support. Okay. Now take this case and you have 3 number of joints here, 1, 2 and 3. So your total degree of freedom will be 3 into 3 will be 9 and you have number of reaction, that is you have 3 number of reaction and here you cannot pull this beam upward or pull this support in horizontal direction. Why? Because you have another support here, so that it will not allow to move this joint. What can happen is you can have a moment. So moment is possible. You have 1 number of support here. So totally if you are adding, how many supports are here? 3 plus 2 plus 1. It is 6. Okay. How many degrees of freedom? You have 3 supports into 3. So 9 minus 6 will be 3. So kinematic indeterminacy is 3 for this case. So what are the kinematic indeterminacy? You can able to move this structure horizontally and At this support you have a moment is possible, and at this support a moment is possible. So these are the possible ways. Okay. Then you have kinematic indeterminacy equal to 4 here. You can write according to the formula. You have number of support which are 1, 2, 3 and 4. So 4 supports, 4 into 3 which will be 12. How many reactions are here? This is a hinged end, hence you have 2 number of reactions. So 2, 4, 6 and 8. So 8 number of reactions are there. So 12 minus 8 will be 4. Where are these possible kinematic indeterminacy? At each and every joint you can have a rotation. So a rotation is possible. Hence this structure is kinematically indeterminate to 4. So find the difference between static indeterminacy and kinematic indeterminacy. So kinematic indeterminacy is number of movement which are possible to a structure, and static indeterminacy says that how many number of support reactions are here when comparing to equilibrium equation. Okay. Now let us take a problem. Analyze the continuous beam as shown in figure by stiffness method. Draw the bending moment diagram. See, you can find the difference between previous problem and this problem. The same type of beam is given. This is a continuous beam. You have a uniformly distributed load at one span, and between B and C you have a point load which is 120 kilonewton, and the distance between this point load and the support B is 3 meter, and same here. So the total span of AB is 6 meter and total span of B to C is 6 meter. Okay. So this is the case. You have to find the bending moment, and by using stiffness method. In the last module they would have asked by flexibility method or flexibility matrix method. So if that is the question, you have to go for the previous procedure. But in terms of stiffness method, you have to go into this procedure which we will be discussing now. First step is finding the kinematic indeterminacy. To find the Ki, the formula I have given, Ki equal to number of joint into 3, that is 3 degree of freedom. So how many joints are here? A, B and C. So 3 into 3 will be 9. So this is your first case, and minus number of supports. How many support reactions are here? 3 at fixed joint, and C is also fixed. Here you have 3 and B is a hinged. Here you have 2. So 3 plus 3 is 6 plus 2 is 8. Your 3 plus 2 plus 3 at each and every joint, and the total number of reaction is 8. Degree of freedom will be 3 number of joints here, and for a joint you have 3 number of degree of freedom. So 3 into 3 is 9. So kinematic indeterminacy is degree of freedom minus number of reaction. 9 minus 8. So which will be 1. Okay, now you have to highlight that where is that 1. So the 1 number of degree of freedom is at the joint B. How I am saying that? Note here, the B is a hinged end. There is a possibility of moment rotation here. This joint can rotate. The fixed joint will not rotate. So it is fixed and it is rigid. So if you apply any moment here, at this joint there will be no rotation. But at the joint B, there is possibility of the bending of the element, and rotation is possible, that is slope is possible. So this is why the kinematic indeterminacy is 1 and it is located at the joint B. Okay. Go to the next step. The structure is kinematically indeterminate to first degree and it is known as independent displacement. Okay. Now you have to locate where is that and write the primary structure. This is element coordinates. Since for matrix method you need to write down the element coordinates. And what is element? A beam is an element. So how many beams are here? AB is one beam and BC is another beam. So you have two number of beams here. So This is element 1 and element 2. Okay. For an element, you will be having nodes at each end. So how many ends are here? 1, 2, 3 and 4. So you have 4 number of nodes. This you have to write and show that you are solving by using matrix stiffness method and the elements are noted here. And next step is writing down the system coordinates. What is system coordinates? You have found out the redundancy, that is kinematic indeterminacy. Where is the kinematic indeterminacy? It is at the joint B. So it is indicated here. So at the system coordinates, whatever might be the problem, you should indicate where is the kinematic indeterminacy. So it is indicated here. Next step is finding the fixed end moment. So write down the step as 3. So step 3 is finding the fixed end moment. So this you know that if a span is having a uniformly distributed load, you have to consider it as a fixed end and the formula is WL square by 12. Your W is 20, L is 6. So minus 20 into 6 square by 12. And the same way you can find MFBA, and for the span B to C, if you consider it as fixed end, the formula is WL by 8. It will be minus and plus. W is 120 and L is 6. So 120 into 6 by 8. So this is your formula. And if you substitute that, you will be getting the answer as minus 60 and MFBA will be plus 60, BC will be minus 90 and CB will be plus 90. So this will be your fixed end moment answer. Okay, now you have to write in terms of matrix the fixed end moment, which is P naught. Here it is indicated as, see, all the notations given here and the letter identification are different. So for flexibility method, you would have found P matrix, which is the final step. Do not confuse with this step. So whatever the letter which are used for flexibility matrix method is separate and this is stiffness matrix method is separate. So here P naught is the fixed end moment. And how many moments are here? You have 4 numbers, 1, 2, 3, 4. So this is why you are writing the element matrix. So you have 2 number of elements, hence there will be 4 number of rows here. So you have a single column with 4 number of rows in this matrix. The same way it is written here. Yes, now we will be going to the next step. This is step number 4. To form the beta matrix, beta is transformation matrix. You have to apply a unit load at the kinematic indeterminacy. Where is the indeterminacy you have found? At the joint B. You have to apply 1 at the joint B. If you try to twist this beam at this joint, what will happen? The beam will bend like this. See, here you will be not having any displacement or rotation, and at this B you will be having some rotation, and P to C you will be having some rotation. So this is called kinematic indeterminacy. So if you apply a moment here, both the beams will get deflected. So if you apply clockwise moment, so this will go upward and this will go downward. So imagine that you try to twist this beam at this support. A to B will be 0, you have no rotation here and you have 1, and B to C you have 1 and C to B you have 0. So this is your transformation matrix, 0, 1, 1, 0. In terms of stiffness matrix, you don't have minus 1 plus 1. You need not to take that, but for recollecting and better understanding, you compare with matrix flexibility method, you would have written minus 1 and plus 1. So that is the difference between flexibility matrix and stiffness matrix. How many elements are here? You have 2 elements and 4 nodes. So all the nodes are written here, 0, 1, 1, 0. So this is your beta matrix. If you have two number of redundancy, you will be having two beta matrix, column 1 and column 2 likewise. Okay. Now next step is finding the fixed coordinate force, that is F naught. Finding F naught is beta transpose P naught. So what is beta transpose? You have beta here, you make it transpose. So the column is made into row. This will be 0, 1, 1, 0. Now it has been transposed. And what is P naught? This is fixed end moment. You already know, which is minus 60, plus 60, minus 90 and plus 90. These are the values. Now how you can find fixed coordinate? Just multiply this two matrix. 0 into minus 60 will be 0. 1 into 60 will be 60. 1 into minus 90 will be minus 90. So if you add that, you will be getting minus 30. Plus 60 minus 90 will be, if you add, you will be getting minus 30, and 0 into 90 will be 0. So your F naught will be minus 30 here. And next step is force applied at system coordinate. So is any force is applied in the joint? No, you don't have force at the joint. So you have joint A, joint B and joint C. The force are acting only at the members, that is B to C and A to B. If you have any force at the joint B or at joint C, then you will be taking F of F. Now in this case you need not to consider. Next step is finding element stiffness matrix. This is step number 5. And how to find element stiffness matrix? The formula is EI by L 4224. In case of flexibility matrix method, the formula was L by 6 EI 2 minus 1 minus 1 2. But here in terms of flexibility matrix, the formula is EI by L 4224. No negative values are found here. You have how many elements? 1 and 2. So you will be having two number of element stiffness matrix. What is the first element length? Is 6. So EI by 6, 4, 2, 2, 4. And the second element is also 6. And you can divide 4 by 6, which will be 0.67. And 2 by 6 will be 0.33. Likewise, you can divide this. And K2 is also same. You will be getting EI equal to 0.67, 0.33, 0.33, 0.67. And you can assemble the element stiffness matrix. How to assemble? The EI is common here. You can take it outside and you can put a matrix. The first element is 0.67, 0.33, 0.33, 0.67. So it is written here the same way for second element. So the rest of the element will be 0 here. If you have 3 number of beam here, beam span, you will be having 3 number of elements. Additional 1 element will be added here. So likewise. Now let us go to system stiffness matrix. The formula is K, that is capital K. If you go to the previous step, it is element stiffness matrix, which is small k. You can find the difference, and now you have to find capital K, which is system stiffness matrix. Step number 6. How to find capital K? Beta transpose small k into beta. Your beta value is 0, 1, 1, 0. EI, what is the small k? Which is the element stiffness matrix, and beta is 0, 1, 1, 0. Now you have to multiply this row into this column. Likewise, you can do it for all the columns. 0 into 0.67 will be 0, 1 into 0.33 is 0.33, and this will be 0, and last component will be 0. So you will be having 0.33 for first value, and second value will be 1 into 0.67, which is 0.67, and for the row into this third column you will be having 1 into 0.67, and for the last column will be 1 into 0.33. So this will be your answer. and you have this column. Now you can multiply these two matrix. 0.33 into 0 is 0, 0.67 into 1 is 0.67, so 0.67 into 1 will be 0.67, and 0.33 into 0 is 0. So you have to add 0.67 plus 0.67. What is your answer? It will be 1.34 something. Yes, 1.34 EI. So you have EI common here. And how to find K inverse? You have to divide this 1 by 1.34 EI. This is K inverse. Stiffness, system stiffness matrix. Okay. Next step is system displacement. This is step number 7, and it is indicated by the letter U. How to find system displacement? U equal to K inverse. K inverse just now you have found out, which is 1 by 1.34 EI. Here you have to apply that, and F of F you have found in the previous step. F of F and F naught. What is F of F? F of F is 0 here, and F naught is minus 30. So these are the two values. Now you have to multiply those components. K inverse is 1 by 1.34 EI, and it is written here F of F is 0 minus F naught, which is minus 30. So minus into minus will become plus. 30 divided by 1.34 will be, it will be 22.39 by EI. So this is system displacement, which is U. Now step number 8, element displacement matrix. How to find del? Del equal to beta into U. What is beta? 0, 1, 1, 0. This is the value. You know that. And what is U? You have found out here, which is 22.39. If you multiply this, 0 into 22 is 0, 1 into 22.39 will be 22.39, and 1 into 22.39 is the same value, and 0 into 22 is 0. Take the EI outside, and you will be getting element displacement matrix del as this value. Now to find P dash, K matrix into del. What is K? You know element stiffness matrix is 0.67, 0.33, 0.33, 0.67. This is element stiffness matrix, and del you have found out currently, which is 0, 22.39, 22.39, 0. So this will be the answer. If you multiply these two matrix, you will be getting P dash. This row into this column. 0.66 into 0, 0.33 into 22.39, which will be 7.39. 0.33 into 22.39 will be 7.39. So if you add this one, 0.67 into 22.39 will be 15, and 0.67 into 22.39 will be 15. 0.33 into 22.39 will be 7.39. So this will be P dash. The 10th step, how to find final force? P of F equal to P naught plus P dash. So you know P naught, which is fixed end moment, that is minus 60, 60, minus 90, 90. What is P dash? Which is this answer, 7.39, 15, 15, 7.39. So you can add these two components. 60 minus 60 plus 7.39, you will be getting around 52 point some answer. So the same way you add 60 plus 15 is 75, minus 90 plus 15 is minus 75, and this is the last answer. You will be getting 52.61 and plus 75 minus 75 and 97.39. This is your last answer. So you have found out the bending moment at all the elements. This is your moment. 52.61 for the first node, second node, third node, fourth node. So what are your nodes? 1, 2, 3 and 4. So all the nodes are written here with the respective negative moment, and you can find the positive moment by using considering the beam as simply supported. This is a beam which is having a uniformly distributed load. So the formula is WL square by 8. So this is WL by 4. W is 120 into 6 by 4. 120 into 6 by 4, which will be 180, and WL square by 8 will be 90. So your positive moment is 90. Why it is a parabola here? Since you have a uniformly distributed load. Why it is a straight line here? If you have point load, you will be having a straight line as bending moment. Okay. Then at joint A, you got the answer of 52.61. This is your answer, 52.61. And at the joint BC and CB is 75. Hence, it is taken as 75. And at the joint C is 97.39. This is 97.39. So all the moments you got and connect all the points. So you will be getting a straight line. So this is negative moment what you have done by using matrix stiffness method, and the positive bending moment will be taken by using simply supported beam. Consider it as simply supported, you will be getting positive moment. So you can understand that for finding negative bending moment we will be using number of techniques. It might be slope deflection method, moment distribution method, or flexibility fix method and stiffness matrix method, whatever might be, you will be using the different techniques. So these are the different techniques which is used to find negative bending moment only. So the positive bending moment can be found out by using when you consider it as simply supported beam. So the structural analysis here is to find the negative bending moment. So this needs a technique, and you have 5 number of techniques. Either it might be Kani's method, you have 5 number of methods. So whatever might be your method, you have to find the negative moment. So this is your case.